So this is the wind turbine for the Castlehouse project in London, and we opened up the side covers and took the fiberglass nose cone out a little bit so you can see what's happening underneath here. And it's all mounted on this temporary assembly rig that we put it on while we're working here at the site. On this wind turbine, as on most wind turbines, one of the most important things is the blades. They actually catch the wind and make sure the energy is getting into the system. Well, this is just a test blade we put in here for showing how it all works. And as we had to do this design, we were also looking at where to get the blades because no one's actually manufacturing blades this size anymore. And we fortunately found a gentleman that came out of retirement to assist us with this because he had the design on one of these blades, on this type of blades. And then we adjusted the length according to the constraints of the Venturi so it would fit into it. And basically it's made out of fiberglass and carbon fibers. And the first test we did with these blades, we just put a static load on and found out, okay, how strong is this blade? It was quite strong, but we would like it to have a little more reinforcement. So we added another 8 kilos of fiber for reinforcement on the second test. And then we also added a small Kevlar strand inside it. So in case anything breaks, it still hangs onto that Kevlar strand. But it's so strong now that with the wind forces that in theory could break a blade like that, then the building's actually, it has some different issues than the blades itself because the top of the building's probably not there anymore. In the original design, we started out with a 3-bladed turbine, but we found out from aerodynamics and from acoustics on the building, as this is confined within the Venturi, then it was actually better with a 5-bladed turbine. So we had to redo the design after finding out that one. Because usually a smaller turbine like that has an air brake where the tip of the blade is extended and twisted in the air so it stops the movement instead of pulling. And as we couldn't do this because we have the Venturi, then we had to sort of re-engineer everything here. And we actually did a whole new design on a hub where we basically got the idea of the major offshore or onshore turbines where the entire blade is pitched. And then we just shrank this to about 1/10 of what's usually the size. As a result, we had to have everything made specific for this one because very few components is actually made to these sizes. So for this test mount of one blade, we just made it so you can see how it pitches. So when the hydraulic is either losing pressure or if the electricity disappears from the system, then it actually pitches the blade out. So it turns and then acts as an air brake in the system. And you can see now that it pitches out. So the blade is in a reverse position and it's got this entire surface against the wind, so it now stops. So when we fold the covers down on the turbine here, we have these work platforms. In order to do service and maintenance, we need to be able to access all the components and parts on it. When we open up like this, what we find here is the mechanical brake system, which is the secondary brake system, as the air brake on the blade pitch is the primary brake system. And then the mechanical brake system is the last sort of stop it for the last few meters. Both the air brake system and the mechanical system are sufficient to stop the entire turbine on its own in case one of the other systems they fail. And also the brake calipers themselves are made in a way that they're fail-proof in the way, or fail-safe in the way that you need an active hydraulic pressure to open them. It's not like you have to push on a brake pedal to stop. It's just you need an active opening system from the hydraulics. So in case you have either a hose that breaks or electricity failure, then the pressure is released and the mechanical brakes actually stops the turbine. Contact. So what we did here is that we removed all the covers to show how it looks when it's out in the open, and we now use the generator as a motor to spin it just to see that the functionality is right. And basically the control system is that if it either gets an alarm from the building or vibration, or if there's a power failure somewhere, then it just stops and it goes about this. So that's how fast it stops when there's a power failure, for example. But when it's working, then the main shaft connected to the hub gets all the rotating movement. We got the main shaft coming in, connected to the brake disc, and after the brake disc we got this coupling, which is basically 2 pieces of special made rubber that can sort of flex just a little. So in case there's any discrepancy in the center line between the main shaft and the gearbox, then these rubber connectors or couplings can take that movement. It also acts as a vibration damper, so in case you have any noise or vibration from either the hub and main shaft or from the gearbox and generator, they won't pass through this rubber coupling. The entire system with the mechanical brake and the rubber coupling, we actually copied and shrank from a standard turbine, which is 12 times bigger than this one. So we had a kind of a challenge to get it into this. We've got a few sensors here. One is for ambient temperature, and these two sensors up here, they actually measure that the entire system is spinning correctly. We have two sensors. One is for the main control unit, and the other one is for a safety chain system. They need to be independent because in case the sensor breaks, then it gives a faulty signal to the system, and we need both sensors so we can make sure that it gives the right input all the time. And as one is for the control system, that gives an active input that we can actually use in the control system, and the other one is a passive system, basically for safety. So in case it's a part of the safety chain, so in case something goes wrong in one of these units in the safety chain, then it just stops the turbine completely. And that's one of them. From that on, we got the generator system here, and at the very back we got the hydraulics. And the hydraulics is used for controlling both the mechanical brakes and the air brakes out in the front for the working position or the pitch position on the blades. So from the coupling, the system is connected to the gearbox and the generator, which is a combined unit on this one. One of the issues we had to work with when choosing on the gearbox and generator was actually that as these turbines are working in a fairly turbulent environment within the top of the building, we needed a gearbox that was severely over-dimensioned, and at the same time it had to be very small in order to be inside the turbine. And apart from that, it also had to fit within the weight constraints of the design, because everything needs to be able to be taken apart and lifted down from the top of the building with the building maintenance unit, which doesn't take too many tons. I think it's 500 kilos or 450, something like that. So our choice was this one. We found also by doing analysis on some really old turbines here in Denmark, where we actually found one that'd been working for just over 35 years. And they took it down and had it sitting in a barn, and we disassembled it and found out that it was actually this same company that was still doing these gears. And with a 35-year-old track record, we thought it would be okay. The gearbox and the generator is also mounted to the entire system through these rubber damping units here at the bottom. So from a vibration point of view, the entire system is isolated from the rest of the structure. So any noise from the gearbox or the generator cannot be transmitted into the system. That gave us another challenge, because then it's actually not sitting on a rigid mount, but it's on soft ground. So we had to stiffen some other parts of it, and also accept that the coupling might be able to be a little more flexible in that way on it. Of course, the generator is the part of the turbine generating the electricity, and this one has a maximum rated power of 19.5 kilowatts, which means at ideal wind conditions, then it would actually generate 19.5 kilowatts. In the gearbox, we got this temperature measurement gauge telling us what's the temperature of the gearbox oil, and if it gets over a certain level, it shuts down the entire turbine automatically, and of course sets an alarm for the control system that it had an automatic shutdown due to oil temperature. In the middle of the turbine at the top here, we got the main circuit board for electricity and for circuits, for sensors, and all the valves for the hydraulics. And here at the very back of the turbine, we have the hydraulic station, which is basically a hydraulics pump, and then the control valves and all the pipes going out to the system. So this is generating the pressure, which actually is used for pitching the blades on the air brake, and also for opening the mechanical brakes out in the front. And it's also where we've got the pressure accumulator, so in case there's a power failure on this system, then the pressure for pitching the blades is still kept here, and since the valve then opens when the system is gone, then the blades are pitched, and the mechanical brakes, they just close in on the disc brake because the pressure is gone from it. Here at the back, we also got a vibration sensor, which is sensing if the entire turbine is vibrating due to anything that went wrong on it. It can also be just because of turbulence in the Venturi. Then if the entire system starts vibrating, then the sensor says, okay, there's a vibration over a certain level, and then it just shuts down automatically for the entire turbine. It's going to be good to see them up there.